And let's get going. All right. So, any questions? While I'm just going to give a quick overview of Newton's laws. Any questions come up during it? Feel free to. I got the chat window open. You can go ahead and pipe right up. Um, then we're going to do what we normally do: a little bit of polling. Just two questions today. I'm going to work a couple problems, and of course, then you're going to work a couple problems because that's what physics requires of us. I'm going to share this screen with you, which should be my PowerPoint. Share it. Yep, there's the green border. And we're going to talk today mostly, there'll be some discussion of second law, but primarily Newton's first law, the law of inertia. Remember, object at rest stays at rest, object in motion continues in motion with a constant velocity, both magnitude and direction, unless there's some external forces which don't add to zero. And so the way we say that is if the sum of the forces are zero, then the object is either at rest or moving at a constant speed, a constant velocity, not changing magnitude, not changing direction. That's the problems we're going to be working mostly today. We call this the law of inertia. Inertia is a quantity associated with any object. It's the bigger the inertia, the bigger the object's resistance to any change in its motion. Equilibrium, those are the two conditions we talked about, either at rest or moving at a constant velocity. Newton's first law. Engineers take a course called statics. Objects are at rest typically in a statics course or moving at a constant velocity, and they learn to do those calculations in great detail. Second law says the acceleration of an object is directly proportional to the force that you applied, the net force. So if there's multiple forces, you have to add them up. And that often is the holdup in a physics problem, is being able to add vectors. And I'll talk about some resources here in a bit about that. It's inversely proportional to the mass, that measure of inertia, and that's that quantity that we discussed. The bigger the mass, the bigger the inertia, the more resistive it is to any change in its motion, any acceleration. And of course, since these forces and accelerations are vectors, the direction of the acceleration is in the direction of the net force once you do the vector addition and you find it. And of course, vector addition is most often done using components, a skill that you just have to be able to do. We've spent, I guess, 2 days talking about vectors out of the 12 we've met. And so from that, you have to believe that's important. And I did see as I was grading worksheet 4.1 that for some people that's a skill you need to improve on. Okay, and I have a resource to help you with that we'll talk about in a bit. All right, so the way we mathematically state Newton's second law, and we'll talk more about problems with Newton's second law on Wednesday. That is the full subject for Wednesday. You sum up all the vectors, that sigma letter right there, the Greek S capitalized, okay, looks kind of like an E. That means take the sum of all the forces, add them up as vectors, okay? Have to be able to get components, have to be able to add the X components, add the Y components. And then of course you divide through by the mass, and that gets you the acceleration. So that's the equation we write. We often solve for the sum of the forces and say it's equal to mass times acceleration. Sometimes you'll hear me talk about the left-hand side where you sum up the forces. That is the sigma F. And the right-hand side, the object's mass times its acceleration. Is how the construct we use when we're doing these problems. All right, just a bit on units, because that's never important, right? Sarcasm there. Length, mass, and time, okay, are our fundamental units in a mechanics course like Physics 1. We talk about length in meters, mass in kilograms, time in seconds. And I refer to that as the MKS system. Other disciplines like chemistry, I don't know what biology uses, to be honest with you, just on the scope of my understanding and knowledge. But for disciplines that look at smaller things than physics, centimeters, grams, and seconds work as well. And then, of course, we talked about acceleration in chapters 2 and 3. And acceleration is a meter per second squared. A velocity is a meter per second. In that SI unit system that chemists use, it's a centimeter per second squared. But then most important for chapter 4 and chapter 5 now, Newton's second law, that force is equal to mass times acceleration. Well, the unit name we give to a force is a Newton, okay, and that's a kilogram times a meter per second squared, a mass times an acceleration. And in that other system that the chemists like to use, there's another unit. It's called a dyne. I think it's abbreviated capital D, but just not something I use. It's so short, I just always write out dyne whenever I have to use it. And it is a gram times a centimeter per second squared. All right, here in the United States, we don't conform with the rest of the world, and so while the roots of that last column on the right there are British engineering units, okay, we've adopted them in the United States and we've stuck to them when the rest of the world went to the SI system. But we still use feet, we still use seconds, we still have accelerations in feet per second squared. The unit of force in that system is a pound, but it's a little bit duplicitous in the sense that sometimes people refer to pounds mass. The true unit of mass in that system is something called a slug. And so then a slug times a foot per second squared is a pound. But as I said, people often talk about pounds mass as well and just kind of fudge the accuracy of units. If you are trying to relate a pound force to a pound to a Newton, you can see the conversion factor there. 1 pound is just about 4.45 newtons. Nothing you should memorize, but just be aware you can convert between those with a simple conversion factor. All right, so the big picture, if you're working a problem where objects are at rest or moving at a constant velocity, Newton's first law, sum of the forces are equal to 0. If they're not, the sum of the forces don't seem to come to 0, then you're going to get an acceleration, and the sum of the forces will be equal to the mass of the object times its acceleration. And yes, some people do consider Newton's first law to be a special case of the second law when the acceleration is 0. That's a perfectly legitimate way to see it. And in some problems, you may find that in one direction, like the horizontal direction, the sum of the forces might be equal to the mass times acceleration. And then in another direction, like the vertical direction, the y direction, the sum of the forces might be equal to 0 because there's absolutely no motion in the y direction. And that's possible in a problem. You might have to apply both laws. Some assumptions on our models. When we get these problems where we have skiers and people jumping out of airplanes and all that. As we said, I think on the second day of class, when we treat complex objects as dots. It's a basic physics course. We're modeling things as simply as we can. All our surfaces are frictionless, and there is no drag through the air unless we tell you otherwise. The problem should always specifically leave you no doubt that friction and drag are something you have to consider if they're present. If it doesn't mention them, you can just assume they don't exist, and it makes your problem a whole lot simpler. All objects in life have mass, including strings, ropes, springs. In a basic physics course, we consider them to have no mass. Okay, and so we don't add them on. If a rope has some mass, we don't add it on to the mass of an object in a physics class. We just ignore it. And you take an upper level physics class, you might actually go and use a mass for a connecting object like a rope. In an introductory course, we just pretend it's 0. The tension in a rope is the same everywhere. Okay, that goes along with the fact that it has no mass. If it's hanging vertically and you realize a rope could have mass, well, you'd expect maybe tension to be greater at the bottom than at the top. We don't do that in the introductory course. The tension in a rope is the same everywhere. And remember, one of the laws you've heard about physics, you can't push a rope. Well, that's true. Ropes aren't stretchy. They don't extend out. So 2 objects connected by a rope move together. Okay, you don't have to worry about elastic ropes in this class. And you saw in the example I did last night with the traction problem, it had a couple pulleys in it. All the pulley does is redirect the tension. Okay, we assume for now, we might change this a little bit later. In fact, we will a little bit later. All the pulley does is redirect the tension. And so those are kind of our model assumptions. And if any of those things bother you, those are the kind of questions you can always ask on an exam or a quiz or even a worksheet. Hey, what's my assumption here on this problem? Do I have friction or not? And there are key words like the surface is rough, the surface is smooth. Rough means there is friction, smooth means there's not, things like that. And you just have to pay attention to those. All right, problem solving approach that we talked about on day 1 applies more than ever with these Newton's first and second law problems. Read it, write down what's given, write down what you're finding. That 4th bullet, a sketch. I'm always concerned when people don't draw sketches and then they just start plugging numbers in for symbols without really understanding what each number and what each symbol represent. And it's a lack of visualization. And that becomes more of a conceptual error. That's not a small mistake in a physics problem. Okay, we call these sketches in Newton's second law and Newton's first law problems free body diagrams. You need to have some idea what your coordinate system is. You should just make an attempt to specify what it is. And then, of course, the skill that we said about vectors, you have to resolve forces into coordinate systems. You write down whether it's Newton's first law or second law, okay, one or the other. It could be both if the problem has, as I said earlier, Newton's second law going on in the horizontal direction, Newton's first law going on in the vertical direction. You manipulate the equations with algebra. That's the second big math skill that you need to do, because often there might be two equations with two unknowns, and you got to be able to solve that system just like you would in an algebra class where you don't know X and Y. You have to see that pattern in your head and work it. And I'll be doing an example like that today. Then you kind of check your answer, make sure it makes sense. And so if you go through those steps, and I did show you that, I gave you a worksheet that's one of the resources in Canvas. If you know, that isn't just a normal pattern to flow through as you work through a problem because it's kind of imprinted in your mind, open up that document and just kind of use it as a guide as you're working out physics problems. All right, here's the first polling problem then, and it demonstrates, I think, one of the things I said, that you have to have some math skills in place, right? And so we'll launch this poll, and hopefully you'll see it. And so you got to be able to get vector components, and you'll see that the vector is 10 newtons in both cases, and the angle's theta. So go ahead.
I'm getting a different question.
Yeah, the poll doesn't match.
Oh yeah. Sorry, let me fix that. Yeah, sorry. The ABCD, you might need E. So let me end that. I got me hitting the wrong buttons here. All right, I got to go all the way. Yeah, it always puts it at the bottom, and I expect it to be at the top. There we go. That should be hopefully the right one. 511, 511. Yeah, they match now. Sorry about that. Oh, and that little question mark thing, that's theta. Zoom doesn't know the Greek alphabet, so when I tried to type in a theta right there, it gave me a question mark. All right. I can just tell you as I'm watching it, with 19 people in, we're split. The majority do have the right answer, but we're split with a bunch of answers here. Always concerning, but this is about time to talk about that resource I have for you. 26, 27, 28. All right, everybody's in. We'll end it, and I'll share the results with you. And you can see E there is the correct answer, and the majority got it. You might say, oh, that's awful hard to be doing that in my head. I think, let me get a pen here to annotate this. Just look at one of the forces, say one of the 10 Newton. I tend to like the one that goes off in the first quadrant. Okay, so that's 10 Newtons. Okay, and let's see, it has two components, right? The angle theta is given as that angle right there with respect to a coordinate system that I haven't drawn, but I'm kind of thinking that's the x-axis and that's the y-axis. And this is the math skill that you have to have in a physics course. Without it, the course is going to be very frustrating. And so my advice, here we are in week 5, we've spent a couple days on this. If you don't have this skill down well, and I can see a good 12 of you, about almost half, you got it. For the others who aren't seeing this right away, the Quantitative Skills Center that is in the basement of the library, but we'll be holding virtual classes. This is a place to go. You can come see me in office hours. Certainly, I'll help you with this. But the Quantitative Skills Center has two of my actually one of my current students, who I also was a former student, Max Tucker and Anna Hall, who's one of my former students, on Tuesday nights. I think Max told me it was either 8 or 8:30. They'll be there to help you with math like this. Okay, this and perhaps the other thing, the two equations, two unknowns. And I recommend Max and Anna. They're both great students. They can help you get components of vectors. They can help you solve two equations and two unknowns. So that's my first resource. If you can't do what I'm about to do with regularity of getting it right, well, see Anna and Max or see me, because you have to be able to do this. Any event, so now to the answer. Where's my pen? Oh, it always does that. I lose my pen. Let me escape out of that. It's not going to let me escape. Yeah, this is one of those things with Zoom. All right, where is my pen? All right, come on. Oh, there it is. I just saw it. It's up there. There it is. I got to get it down here. All right. I don't see a there it is. A little lower. There it is. Almost there. All right. There it is. So I'm trying to get that component and that component. And let's see. There's a right triangle that's formed there, because I can use that head to tail method, and I can draw the Y component right there. So that's 10 newtons. And to get the Y component, I guess it's the opposite side of that angle. So I got to multiply by the sine of theta. Okay, and that gets me the Y component of the 10 newtons. The X component, of course, is 10 newtons times the cosine of theta. Well, there's two of those vectors, right? Let's see if I can get it over. Yep, there it is. So there's a vector Y component right there from the 10 Newton that's going off to the right. There's another 10 newtons times the sine of theta right there. There's another Y component of the 10 newtons. And so since this thing's at rest, those two components, 10 newtons times the sine of theta from each of the two 10 Newton vectors, have to balance off the force because they're at rest. Two of them are up, one of them's down, the force itself. And so that force must be equal to twice 10 newtons times the sine of theta. Now, you may ask, what about the X direction? Well, of course, the X direction, the force that's going up and to the right, has 10 newtons times the cosine of theta in the X direction. And the force that's going up and to the left, it has an X component of 10 newtons times the cosine of theta, but it's to the left. And so it's negative. Those two add to zero as well. And that allows this, this object to stay at rest. All right, now I got to find my tension, or find my pen right here, and get out of annotate. Polling, pause, so I can get my, where is it? I had it there. All right, there it is. Participants, polling, share, pause, annotate, and get out of annotate, please. Come on. Not going to let me do it. Up there, I got my cursor back so I can move on. I can stop sharing, and I, with a cursor again, now I can go, there's my answer, in case there was any doubt. There's my explanation. And let's move on to the next guy here. Did I share it with you? Yeah, the majority got it right. Stop sharing. Let's see. Move on to the next poll. Come on, cursor. Play along today. No. There we go. All right, and I'm going to try and clear the, oh, it's always dangerous though. Where to put the, maybe it's because it's up there. Yeah, let's launch it. And I'll try to get rid of all my scribbles here. But you see the box is being pulled to the right with some tension. And we're asking about the normal force here. How does the normal force compare to the weight? There we go. Okay, now it's, I can clear my drawings. There we go, get rid of that stuff. All right. About 24 people in, 25, and the majority are getting the correct answer here. So that's good. 27, two more. Not sure we're going to wait. All right, could be an internet issue for those two. So I'm just going to end the poll and share the results. And the majority of people think that the normal force is less than the weight. Okay, I'm going to jump out of the screen, the presenter view here. It's easier to draw that way. And where'd my poll results go? Ah, so there it is. We're screwed. And so I'm going to just draw a free body diagram here with a better cursor that isn't going to lock me up. All right, so free body diagram. There's the mass. Okay, it has weight. And it has a normal force. And then this tension force, which is pulling up and in this direction. And again, we don't give you the angle here, but you have to be able to visualize and in many cases calculate, okay, there is the tension's x component. There's the tension. Remember, the tension itself is always the hypotenuse of the right triangle, okay? So if I was to give you this angle right here, that component would be the tension times the cosine of that angle. Then there's a vertical component to the tension. Not sure why I didn't draw that one dashed, okay? And that is the tension's y component. And of course, if I've already used the cosine of theta over here, tension y must be the tension times the sine of theta. Again, you got to be able to get that right. These two components mean I don't need the tension anymore. I've got its two components, the x and the y component. And you can see that in the y direction, the sum of the forces are equal to a normal force up plus the y component of the tension is up, the weight is down, and in the y direction, the sum of these forces has to be zero. The object is stationary in the y direction. It is a Newton's first law problem in the y direction. And so I guess if you solve for the normal force, you find that it is equal to the weight minus whatever the tension's y component is. So as long as that's non-zero, well, then those of you who said part C, that the normal force must be less than the weight, are exactly right. By how much is it less than the weight? By whatever the y component of the tension is. Good to go there. So all of you got that, picked it exactly correct. And I have no idea where polling went. It's being hidden by Zoom on me here. So hopefully I can't share the results to see, but about half the class got it right, but about half didn't. Okay, and it's probably because of the inability to draw this free body diagram. And of course, if you needed to find out the number, the numeric value, tension in the y direction, it would be tension times the sine of the angle theta. Okay, got to be able to get that. All right, yeah, so less than. I'm going to do two problems. I want to start off with this object. This is going to be the first. It's our third example after the polling. There's no poll here for this, but I'm going to shift over and actually work this problem. And you can see I got this bomb. This is just a mass, okay? And it has some weight. And on Wednesday, we'll actually learn how to calculate that 50 newtons of weight that that object has. It's hanging from two cords which are attached to the ceiling. And theta 1 and theta 2 here are just the angle that the cord makes with the ceiling. And one of them, the one on the left, the theta 1 is 30 degrees. The angle on the right is theta 2, that's 45 degrees, not exactly drawn to scale. But you can see that our problem is going to be to figure out what are the tensions. And I've labeled the tensions T1 and T2. And hopefully that's a sensible thing to do for you. Okay, so let's see. What do we have to do with this problem? Well, you can see I took my mass and I drew a free body diagram right here, approximately right. Drew the tensions, maybe that just make that theta 2 look a little bit more like a 45-degree angle. But this object is at rest. And since it's at rest, the sum of the forces have to be equal to zero. And of course, last week we worked on adding vectors. And sometimes the sum of the forces didn't come out to be zero. Sometimes it does. In this case, they must come out to be zero. And so that really means two things. The sum of the forces in the x direction, the horizontal direction, have to be equal to zero, just like on that ring that we were working with a little bit ago. And the sum of the forces in the y direction has to be equal to zero. Mathematicians introduce a lot of shorthand. And this vector symbol here is a shorthand. It tells you that I got two equations, okay? And you have to be able to work those equations one at a time. You can't just work the vector equation in and of itself. You got to recognize that that's shorthand because we were too lazy to write out the sum of the forces in the x direction is equal to 0, sum of the forces in the y direction is equal to 0. And that's how we have to solve this problem. And so clearly what I'm gonna have to do here is take tension 1 and tension 2 and get their vector components. And so that's what I'm going to do on the next slide here. Come on, advance. You can do it. Oh, maybe it can't do it. Maybe I'm going to have to go to someplace else. Yeah, because Word has decided it doesn't like that one anymore. Yeah, we're getting all kinds of technical problems today. All kinds of technical problems. So I'm going to shut down PowerPoint because it's holding me up here. And I'm just going to switch over to sharing my iPad screen with you. Yeah, go away. I don't want to do that right now because I got the same problem. I'm just going to have to show it to you in a little more detail here with my pen. All right, so share my iPad, share that. Let's screen mirror here. That seems to be working. And there it is. Hopefully you're seeing the same problem now on my, from the worksheet problem today, because that's what it is. And I need to do a little bit of drawing on this that I was hoping to show you in PowerPoint. Okay, so what I'm going to do is I'm going to take T2 first here, and I have to get T2's x component, and that would be T2 times the cosine of theta 2, because we made that angle right there, theta 2. Shift the glasses over here so I can see a little better. All right, so hopefully that's something we've said multiple times today. You get the idea, it's important. There is the y component, T2 times the sine of theta 2, which is equal to the y component, T2's, come on, pen, y component. And you know, you have to be able to sketch that out. Similarly, I guess, if I look, and I'll change colors here just to denote the thing on the T1. T1 is going this way. I almost like the way that looks better. There is T1's y component, okay, and the angle theta 1 is right there. And so that would be T1 times the sine of theta 1. And of course, the x component, T1 x component, is equal to T1 times the cosine of theta 1. And I'm hoping those two are readable, reasonably readable. And so what do? We look at the two components of force in the x direction. And to be specific, T1 x component is moving to the left. And so I really should make it negative. And that's why that negative sign is right there. Okay, you can make it negative here if you want, and then add it in as a negative number. You just have to remember that that component is going to the left, so you make it negative, and that's that thing. And then the other one, T2 cosine of theta 2, it's to the right, and change colors back. What color was I using? I guess I was using that one. That component is going that direction. And so those two vector components are what give me the sum of the forces in the x direction. All right, well, similarly, in the y direction, I have T2's y component going up right there, and change colors here, T1's y component going upward right there. And of course, I've figured out what those two are. T1 sine of theta 1, T2 sine of theta 2, I added those together. They're both upward, and that's why they're both positive. And then, of course, the weight of the mass is pulling downward, the weight of that bomb there, pulling downward. And so that's why I made it negative. Remember our rule, any vector that's in the same direction has to have the same sign. Any vector that's in the opposite direction has to have the opposite sign. Okay, so we're on a roll here now. We've got two equations, and as you can see, I got two unknowns, don't I? I don't know what tension 1 or tension 2 are, but right here, two equations, two unknowns. Let me slide up to give myself a little more work here from those equations. And let's see, I know what the angles are though, so why don't I fill those in? My x equation, and I'll switch over to work in blue here while we're doing this algebra. The x equation tells me that, well, if I bring the negative one over the other side of the equation, put it with the 0, it would be t1 times the cosine of theta 1 is equal to t2 times the cosine of theta 2, right? And I know what those angles are. So that tells me that t1 times, let's see, that's a 30-degree angle. Cosine of a 30-degree angle has to be equal to t2 times the cosine of a 45-degree angle. Now, I want to make a quick comment on these angles. You notice here, this is, I think, the second or third time in a row we've looked and the x component was cosine. And that's always true, provided that the angles are given with respect to the x-axis. Be careful about memorizing a rule like x is always cosine. I've seen students do that in the past. It is x, the x component always gets the cosine as long as the angle is specified with respect to the x-axis or the minus x-axis. If we ever do a dirty trick on you and make the angle, give you an angle with respect to the y-axis, well, then the x component becomes sine. And so you just have to, maybe that's a rule you memorize. Fine with me, but my preference is you would just do the trigonometry. Okay, you know, I don't need a calculator completely for this. The cosine of 30 degrees is just something that I know. A cosine of 30 degrees is 0.866. It's the square root of 3 over 2. You may have picked that up in high school. You may not have. If you don't know that, just go to your calculator at this point. And that's equal to T2. And the cosine of 45 degrees is 0.707. Just use it enough, you know that. That's also the square root of 2 over 2, right? And so there's my one equation, but I got two unknowns in it, so I'm kind of stuck a little bit. All right, well, I can do the same thing with the y equation then. Let me slide up. Hopefully I got a little bit more room here. I'm going to insert, maybe not. We'll work over on the side then. So I can do the same thing with the y component equation. And so we'll take this guy over to here. And let's see, so I'll just have to write a little bit smaller. That says that T1 times the sine of 30 degrees plus T2 times the sine of 45 degrees minus the weight. Now, we were given the weight here, weren't we? Minus 50 newtons. Well, I'll put the 0 out front. All of those have to add up to be 0, right? Okay, good to go. I'm going to bring the 50 over to the other side of the equation with the 0. So 50 newtons then, because it's negative, it's a handy thing to do, is equal to, let's see, T1 sine of 30 degrees is a half. So that's T1 times 1/2, okay? And then again, the sine of 45 degrees is the same as the cosine of 45 degrees. It's 0.707, square root of 2 over 2, square root of 2 over 2. Okay, and so now I have a second equation, but that's all right because the same two unknowns occur in the second equation. And then the answer, the problem is, can I solve for this? Well, you know, there's multiple ways to do this. And again, I would refer you to Max or Anna if this isn't something in your math toolkit. But I do notice that this guy right here and this guy right here are exactly the same. And so I said, well, I can substitute in then. So 50 newtons is equal to T1 times a half, okay? And I can add to that T1 times the square root of 3 over 2, right? And now I've got one equation with one unknown. My goal there is to eliminate one of the unknowns. I eliminated T2, and I get that. And I can just run that to my calculator right away, factor out the T1. So it's T1 times the quantity 1/2 plus the square root of 3 over 2. That number is actually 1.366 if you care. So I take 50 newtons then, and then I'm dividing it by the sum of 1/2 plus the square root of 3 over 2, which is 1.366. Get it from your calculator. And what I got for that then is 36.3 newtons. That's T1. Okay, of course, once I got T1, I just take it right over to here and I plug it into the other equation, and I can quickly solve then for what T2 is. And T2 would then, the twos cancel here, don't they? T2 is going to be equal to T1, and I guess it'll be the square root of 3 over the square root of 2. And I plug that into my calculator with 36.3 for T1, and I get 44.8 newtons. Okay, the reason I like this problem, it's challenging, certainly, and I wish my handwriting with this stylus was better. Uh, but what it does do for us is it makes us get components of a vector because you have to solve this problem. It's one of the prerequisite math skills. And then you work the problem in both the x and the y direction, and you work the problem in the x and the y direction, and you get two equations, the two boxed equations there, but they have the same two unknowns. And then you have to apply ninth grade algebra for whatever way you use to eliminate one of the unknowns to solve for the other. And then once you have one unknown, you plug it back in and you get the second unknown. And so it is conceptually fairly straightforward, but mathematically, trigonometry and algebra come into play. Any questions on that problem? All right, then I'm going to move on to the next problem I'm going to do here this morning. Let's move that guy. And it's an inclined plane problem. We've done that a lot. And remember, when we work in an inclined plane problem, it's often convenient to use that as our coordinate system. Okay, and so everything I do here is going to use that as my x and y axes. Okay, and I guess I got two objects here. And so there's mass 1, which has its weight. There's a string 1 right there, and a normal force. And so I'm going to draw it. And although, let's see, the normal force is that way, and I better call it normal force 1, right? Because it's on mass 1. There's a normal force for object 2 here. There's a weight for object 2. There's a weight for object 1. Let's see, there's a tension on this one, call it tension 2 since it's rope 2. Notice that there's also a tension 1 pulling the other way. And on the first guy, there's only a tension 1. Okay, so now I'm going to draw it the way we often draw things. Let's make y upward. So there's normal 1 from the first object. There's tension 1, and you can see they are 90 degrees apart, right? When I rotate it back to a kind of a conventional, there's weight 1, right? And I guess what you have to be able to identify is where the inclined plane angle is, and the 20-degree angle is right there. Okay, and so let's see, the second object has normal 2 pulling up. Okay, it has tension 2 pulling that way. It has tension 1 pulling that way. And it has a weight. Now its weight, object 2, would be right there. And again, you've got to be able to see where the 20-degree angle is, and it's right there with respect to the vertical. All right, and we're going to, I suppose, prove a point here. Now, these objects are at rest, right? So in both these free body diagrams, the sum of all the forces must be equal to 0. So let's work object 1 first. If you look, we're told what the values are. The weight here is 45 newtons. That's a Newton. We're not told what tension 1 is, and we're not told what the normal force is. All we have to find, though, is the tension in that string. What is the tension in string 1? So let's go about doing that. And I'm going to look at the two components of my weight here. Weight 1, its x component, would be equal to the 45 newtons. And then the question always is, well, which trig function? Notice the angle is specified with respect to the y-axis. And so the x component is the opposite side to that angle. So I multiply by the sine of 45. Okay, remember I said you don't always want to memorize x is cosine, because this is a case where the angle is given with respect to the y-axis. And so the x component is 45 times the sine of the 45 of, what am I writing, 45 there? Not a 45, almost a point for somebody if you piped up in chat there. That's, what's my angle? 20 degrees is the inclined plane angle in the diagram shown right there. Okay, and of course, weight 1 y component is equal to 45. If you get one right, the other one must be cosine of 20 degrees because it's adjacent to the 20-degree angle. Okay, well, I think that gives us some good information because I can look, let's see, the tension is in the x direction. So the sum of the forces in the x direction, let's see, it's a tension to the right, and the x component of the weight is to the left. Now I haven't drawn it, but it's right there. It's what I calculated right there. There is a component right there, and it's not moving in the x direction, so those two things must be equal to 0. You can see right away that tension 1 is just equal to the x component of the weight of that object. And let's see, 45 times the cosine of 20. I took that to my calculator. As I was grading, I saw a lot of people, your calculator's still in radians, so you're getting an answer with radians. This is 20 degrees. Make sure your calculator's in the right units. And I got, oh, wrong. That's the other component, not a 4. I got 15.4 when I put that in there. Newtons. And I did the other one just for completeness, even though I don't think I need it to answer the question. It's 42.3 newtons. Okay, so my answer for tension 1 is 15.4 newtons. Since I bothered to calculate that, though, let's look and see, well, what is the normal force? Even though it wasn't asked, it's pretty straightforward to get it. If you look at the sum of the forces in the y direction, well, it's going to be the normal force up minus the component of weight, the y component of weight, and that has to be equal to 0. And that tells you immediately that the normal force is equal to the y component of the weight, which is 42.3 newtons. So although not asked, we could get that pretty easily as well. All right, let's look at the second question then. What's the tension in string 2 now? Okay, tension in string 2. T2 is what I'm calling it right here. It's that guy right there, that guy right there. If the weight of mass 2 is 10 newtons. Okay, I guess the sum of the forces in the x direction, and that is on mass 2, object 2. Over here, I was summing the forces on 1, so maybe I should have subscripted that to make sure that I was using the correct forces. That's the sum of the forces on 1. Now I'm looking at the sum of the forces on x2. And you can see I've got, from looking at the diagram, tension 2 pulling to the right, up the inclined plane, minus tension 1 pulling to the, in the other direction, to the left. That's why I made it negative. And then I also have, I guess, pulling down the inclined plane, the component of weight, that's weight 2's x component. All of those, if you look at the free body diagram, are acting along the x direction. And I haven't drawn the weight's x component, but there it is, and there it is. There's the x and the y component. And so there's the weight's x component, and that's the weight of 2, of course. Okay, and so I guess I'm trying to find the tension in the second cable 2. So these are equal to 0. Ran out of room, so we'll put equal to 0 right there. Bring the other terms to the other side of the equation, so it becomes plus T1 plus the x component of the weight. I think we're good there. And let's see, T1 we know, right? T1 we know because we solved for it right here. It's 15.4 newtons. All right, and then I guess I need the x component of the weight of T2, and so that's going to be 10 newtons. And then here's always the question, which trig function? Well, hopefully if you got one right, you can see it is indeed the sine of 20 degrees for exactly the same reason, okay? And if I work those two numbers in my calculator, those two things, 15.4 newtons plus 10 newtons times the sine of 20, I get 18.8 newtons. All right, I didn't put the 0.8. Come on, eraser. There it is, 18.8 newtons. And that's the Y component. Now, the last thing I do, making sense of this, do I have 3 digits? Well, I have 45 newtons, that's 2, then 10.0, that's 3. Yeah, if you're concerned in both problems, I guess this is probably best stated as 15 newtons, and this is probably best stated as 19 newtons. And I don't, thinking back, I don't know that I was rigorous enough with that on this problem here. What was I given? I have 3 digits. I have 3 digits. Oh, but 50 newtons. If only it had been, yeah, this one probably ought to be rounded as well. So if that was a concern to you, probably true. 45 newtons here, and this should probably best be 36 newtons. If only we were given 50.0, I could have kept the 3 digits. All right. Hey, that's a lot of work for the Y version. Yes. Okay. And yeah, good question. I didn't go on for completeness. And I think you're asking, Everici, about on mass 2 here, right? Or mass 1. Which one are we looking at? Let me see what I haven't done yet. Yeah. Okay. So yeah, I would go N2 minus the weight of Y2's, its Y component of the weight, and set that equal to 0. And so, yeah, I think then the conclusion is similar to 1. If somebody had asked you what's the normal force from the inclined plane on mass 2, it would absolutely just be the Y component of weight, which I didn't bother to solve just because of time. And I can see that my time is elapsed. And as much as I wanted to give you time to work on this, I spoke too long, I suppose. But I'll tell you, the next 2 problems you have to do, and these are for Wednesday, because the homework this week is much shorter, so I guess I don't feel guilty about that. You're just going to do exactly the same problem, only you don't have the issue of components, because you can see that in problem 3, the tension is being pulled directly up, the normal force is directly up, the weight is directly down, and the question is, what's the normal force? So very similar to Eberici's question, only you've got one other force in the Y direction. You got the tension to contend with. So add those forces up. It is a Newton's first law problem, and set it equal to 0. This one's, the 4th problem you've got to do is similar to what I've been doing here. I'll just help you with the free body diagram, and then we'll call it a day here. And it looks like I have 2 tensions. I have a tension that's going up in that direction. That's supposed to be a straight line. And you know that the angle, let's draw the angle where it really belongs, okay? You know that the angle on this one is right there with respect to the vertical. And if you don't believe that, go back to like 10th grade, whenever you learned geometry. Those are 2 parallel lines cut by a transversal, which is that string, okay? And these are alternate interior angles. So that's why the two angles are 20 degrees. So that gives you a clue as to how to get the components of that, because I think you're going to need to, okay? You don't know what that tension is, and you're going to have to figure something out here, okay? There's the weight, and you're given that. The weight is 50 newtons. And then, of course, there's this other string right here, which is pulling that way. I labeled them, and you can label them whatever you want. A and B, 1 and 2, George and Ringo. I don't care what you call them. They just have to be different, right? Because you'll confuse yourself if you make them both tensions. So in my mind, this was 1 and this was 2. And the problem, of course, given that 50 newtons, given that 20-degree angle, asks you to find that. Now, this ball isn't moving. So that must mean once you get the components of T1, the sum of the forces in the Y direction has to be equal to 0, and the sum of the forces in the X direction has to be equal to 0. And I'll just draw some components in another color, hopefully help you out. T1, there's its X component, right? And there is T1's Y component. And so you can see that T1 Y component of T1 moving upward minus 50 newtons downward has to be equal to 0. So I think that once that gives you a strong clue as to what T1's Y component is. And then you have to do trigonometry backwards in order to figure out what T1 is. And then you have to get the X component of T1. So I guess the first thing you do is you figure out that. and then that takes you to T1, and then that takes you to what the X component is. And you can hopefully see in the X direction that T1X minus T2 is also equal to 0. And so once you get T1's X component, you can answer the question, what is T2? So I've set it up for you. It's 1 minute past class, and hopefully those two clues let you know how to go work that. I'll be around here. I'm going to just stop the recording. I'll be around to help you with those problems if you're going to work them right now. I'll still be back at 10:30 for those people that have to run off to class right now. If you have some questions on this, we'll have the second office hour session right then. Last chance for questions. I'll stop sharing this with you, and you all have a great day, and we'll see you later. Oh, one other resource. I did put an equation sheet into Canvas. Now, the exam will be open book, but that formula sheet is available to you. All right, have a great day, and I'm going to stop recording.